Scene 1, The Discovery of Infinite Rectitude. Welcome to the first lecture of the Wave Mechanics Theory YouTube series for microwave absorption. In this introductory lecture, we return to the absolute origin of microwave physics, the boundary interface itself. For more than half a century, contemporary materials science has worked under a tragic theoretical confusion. It has conflated the local behavior of an isolated interface with the compound behavior of a metal-backed film. Today, we return to classic textbook physics of standard electromagnetics to rigorously derive reflection and transmission coefficients from first principles. Let's prove how boundary conditions work, utilizing two completely independent but mathematically equivalent paths, proving that an interface is a physical device in its own right, entirely independent of any thickness d. Scene 2, Method 1, Node continuity of voltage and current. Our first path is the circuit element route, derived from standard transmission line theory. This methodology is detailed in section 4.2.2.1 of Thomas, Paoloni, and Pi's 2024 Elsevier monograph on electromagnetic composites, as well as Appendix A of Liu's critical 2022 Physica Scripta treatise. If we assume the adjacent medium is properly terminated, meaning there is no backward propagating wave from the other end, so VB x1 plus equals 0, the equations simplify beautifully. First, the total voltage immediately before x1 must equal the total voltage immediately after x1. Second, the total current across the boundary node must be continuous. By solving this system of linear equations using simple middle school algebra, we extract the Fresnel reflection coefficient Rm and forward transmission coefficient gamma_m for the isolated interface. The math is absolute. It proves that the reflection coefficient at an isolated interface is an innate physical property determined solely by the characteristic impedances of the two media. It has absolutely nothing to do with the sample thickness d. Scene 3, Method 2, Field continuity of electric and magnetic vectors. Is the circuit element analogy not fundamental enough for you? Let's take the second, completely independent path, Maxwell's electromagnetic boundary conditions across the split interface. We documented this proof in the appendix of our 2020 Materials Chemistry and Physics paper, equations A13 through A16. By applying Maxwell's equations, we know that in the absence of free surface charges and currents, the tangential electric field Ey and tangential magnetic field Hertz must be continuous across any interface. Expressing these fields in terms of wave amplitudes A plus, x1, A dash, x1, and A plus, x1 plus, and utilizing the characteristic wave impedance of the media, we solve once again. Behold the beauty of physical convergence. The field method matches the voltage-current circuit method completely. Scene 4, Choose truth over peer-viewed cowardice. These two independent derivations prove beyond doubt that reflection coefficients at an isolated interface are determined purely by characteristic impedances, entirely different from a metal-backed film where waves undergo infinite internal reflections. Yet, for 50 years, academic gatekeepers in microwave absorption have used the illogical reflection loss formula, coined in Method X, to claim they matched material impedances to free space. They ignored basic wave superposition and the fundamental boundary conditions of textbooks. Why? Because copying journal tricks to publish is profitable, while sitting with classic monographs is difficult. We don't need peer review cartels to validate physical truth. We need the mathematical courage of middle school algebra and the boundaries of Maxwell. Read Yue Liu's key preprints, SSRN 546, 5615 and 546, 3155, and subscribe to his Substack. Reclaim the primacy of theoretical foundations over mainstream academic bubbles. Thank you for watching.